So we've got a car of mass 2,000 kilograms. It drives over a round hill of radius 45 meters. So that's 45 meter sticks. It's a pretty good hill. If you imagine 45 meter sticks put end to end. And there's not a picture. And so I'm going to go ahead and draw one. So here's our car. It's driving along the road. And maybe there's this hill that it's going to go over. So you have to kind of envision that the hill has a circular arc to it. And looking at it, it's got some radius. Now, maybe in the future, that hill, maybe there's a valley. A valley would be a different arc length, right? Arc circle. And so that could be in the future. Hills and valleys. This could also be a roller coaster, your traditional up-down roller coaster, right? And so write an FNet statement. Oh, wait, that's step 2. Step 1, we should probably do what? Diagram. And so where do we want the diagram? Well, it tells us at the top there. And so I'm going to put my car there on top. Let's draw a force diagram when the car is at the top of the hill. What do we get? Uh-oh. Can't forget the every time force. It has mass, so it has gravity. Gravity always acts down. And so we've got this downward gravity, gravitational force, Fg, right? What else? Car on the road? There's a normal force. Now, here's where this one's going to differ than the loop-de-loop. In the loop-de-loop, the car would go upside down. But when you drive over a hill, you're right side up. So normal force is going to be drawn up. Should it be bigger or smaller than gravity? Not bigger. Smaller, because look, gravity is center seeking, and we want Fn is center opposing. And so if you want to make the circle, your center seeking needs to be bigger. Center opposing needs to be smaller. Yes? Okay. And so any other forces acting on the car? I'll allow one more. It's not going to contribute to circular motion, but if it makes you feel better to have it, I'll draw it in there. Friction. Typically cars on the road, right? There's going to be some kind of friction. And so what kind of friction? Is this like last class, whenever we were doing a horizontal circle and the grip made me go in a circle? Is that the same thing here? Do I need a gripping friction? No, it's a vertical circle now. So gravity is really the one that's going to contribute to the circular motion. And so that shearing, slipping, kinetic friction, if you want to put it on there, would be what direction? Based on my picture, it's moving to the right, V, not on the force diagram, separate. And so the force of kinetic friction would be to the left. But notice it's not center seeking or center opposing. It's not contributing to the centripetal force. It would just slow the car down, okay? Good? Okay, so this is different than the car making a horizontal circle on the roundabout that we did last time. Now that we have a diagram, write the FNet C statement at the top of the hill. And so maybe we want to identify who's positive, who's negative. Again, center seeking is positive, center opposing is negative. And if you're neither of those, so just imagine, we're looking at this vertical axis here. Oops, what happened there? Okay. And so who is going to be positive? Who's center seeking? FG. Who's center opposing? Fn. And what about friction? Neither. I don't want to say 0 because that could be misleading, okay? But it's neither in the positive or negative direction when it comes to center seeking or opposing. It's tangent to the circle, okay? Tangent is parallel to your rightward motion. So it would slow you down linearly, but not centripetally, okay? Okay, so F net C would be written as Fg minus Fn. And some of you, that doesn't sit well. You're like, gravity's positive, normal is negative? What? We've seen this before. You can see this with the elevator type example, right? Depending on how you define the positive direction. If you're going down in an elevator, you could say gravity was positive. Yes. I am recording. I did hit it. Yeah. But thank you. Yes. Okay, so there's our FNet statement. Now it says, what if the car's speed is 15 meters per second when it goes over the hill? What's the normal force at the top of the hill? And so we're going to use that statement, and I'm going to write just underneath it. And so we're solving for normal force. It's negative on the right. So I'm going to make it positive on the left. And so I'd say Fn plus Fnet C equals Fg. And to solve for Fn, I want to isolate it. So I'm going to subtract Fnet to the other side. Algebra, right? And so, not that I'm redefining directions, I'm doing algebra to isolate Fn. So here's our working equation. Fg, mg. Fnet equals MAC with circular motion, right? Centripetal acceleration. One more step there to get our speed. I would plug in V squared over R. Did they give us the mass? Yes, as they should. By the way, like tension, when you solve for normal force, mass should not cancel, okay? And we're solving for normal force here. And so they did give me the mass. We know gravity. They've given me the speed at the top, an actual speed. They haven't labeled it minimum or maximum or anything like that. And then they did give us the radius. So let's plug some numbers in. 2,000 times gravity 10 or 9.8 minus, and if you want to factor out mass, you can. It doesn't save much, so I'm not going to. And then times the speed, 15 given, don't forget to square, over the radius, which at the top they told us was 45. So work it out, and notice, the weight of this thing is 20,000. You're probably going to get a big number, and it's okay. Okay, look at relative size compared to the others. Chances are you don't have one force 20,000 and one force 5. Okay, not in this scenario. Let me know what you get. 10,000 even, okay. And so 10,000, that tells me that your centripetal force was 10,000 too, okay. And so 10,000, the SI unit for normal force is Newton. And so that's the answer right there. Everyone okay? Okay. So then part C says, what is the max speed of the car that the car can go over the hill without lifting off the ground at the top? And you're like, what? Cars lift off the ground? Okay, I know for a fact there are some dips at some intersections in Allen, okay, that if you don't slow down, you're going to go up a little bit. You may not notice it, but you notice the crash back down into the ground, right? It's very bumpy. We would say, oh, that intersection's bumpy. And I know this, I have an older car, so I got to slow down at those intersections, okay? And so max speed at the top of the hill, wait a second, our ball and a string, it was a minimum speed. So again, you can't just memorize and think all circular problems are the same. Max speed, if you slow down, you don't come off the ground. If you go too fast, you really come off the ground. We're finding a special case where the car doesn't necessarily go off the ground, but it's minimal contact with the ground. You're just tangent touching as you coast over the hill, okay? And so that's what I'm going to add here, this without lifting off the ground at the top. Yes, we're still at the top, but you lose, no, I'm going to say you have less pressure with the ground, meaning you just skim across the top. And when you're actually riding or driving, you don't notice this. What I notice is how the impact with the other side, the hill of the intersection is. Less pressure. We don't really talk about pressure. It's not on the formula chart type, but this pressure is the force, okay? And so if you have less pressure with the ground, you're going to have normal force minimizing to zero. So it's similar to the ball in a string. Your tension minimizes to zero at the top. Here, your normal force is minimizing to zero at the top. But instead of an upside down minimum speed, it's a right side up maximum speed. Good deal? So we're still going to use the top F net C. And it would still be Fg minus Fn. But notice they don't tell us the new normal force. You can't just use 10,000. You would just be repeating what you've already done. The max speed is not 15, okay? And so here's that Fn reducing to zero. And so F net C, just like last time, MA, and then centripetal acceleration, V squared over R. To save a little room, I went straight for it, equals Fg, which is again mg. And if normal force zeroes out, what do you notice happens? You don't have to do it. We do know the mass, but here I've got two terms, mass is in both. You could actually cancel out your mass. And so to solve for this V max, again, you got to multiply both sides by R. Hopefully this feels familiar. And then take the square root. That's exactly the same equation we had for minimum speed for the ball on a string. But now with the car on a hill, it's a maximum speed. And so 10 times our hill they gave us was 45 meters. So square root of 450, say it louder, 21.2, yeah, we'll just leave it. 21 meters per second. So previously we were going 15 and we had contact with the ground. There was a normal force. But when normal force, when you want it to minimize to zero, you can actually go faster over the hill. Good deal? What if I went faster than 21? What would be the case if I went faster? What if your actual speed was greater than the maximum speed? What if you drive through that intersection too fast? You would lift off the ground. You would lift off the ground. And the crashing back into the ground when you come back would be that much more damaging. I don't want to damage the car. What if you were less than the 21? What if you were less than the maximum speed? Say again. It wouldn't lift off, But what's the other piece? Would I have a minimum Fn, normal force? I would have Fn. It would be like part B, right? 15 is less than 21. So it'd be like part B, Fn would be bigger than 0. You would feel the pressure. You would maintain contact with your seat. Yeah. When you come back, will you just put the door stop ajar? Okay. Okay. Good on the car on the hill. That's a vertical circle. Now let's go back to number 9 with a horizontal circle. Okay. When he comes back, will you let him in? Just let him back in when he comes back. Okay, so number 9, totally new problem. It's going to be a horizontal circle. A 1,000 kilogram car rounds a curve on a flat road. They did not say hill. We're going back to that roundabout, okay, that we saw on Monday. It's got a radius of 50 meters. That's good. Don't convert. With a velocity of 14 meters per second. Will the car make the curve, or will it skid off the road? Uh-oh, AAA, come get me. And so here, we're given an actual speed and the radius and the mass. How do we know that magical speed, if it's too much or too little? How do we know if we're going to make it on the road or not? Well, we got 2 conditions. It says CD, but it's AB. The pavement is dry, and the coefficient of static friction, AKA static friction, is also the friction that causes you to have grip, right? And so this is our gripping friction. It's 0.6. Or what if it's an icy day? And yes, the condition of your surface changes the coefficient. A little review, coefficients are determined based on the 2 surfaces in contact with each other. So say it's the same rubber tire, but now there's ice on the road, so you should have you should have less grip. Everybody good? And you might make an assumption of what the yes or no answer should be, okay? But let's prove it with physics, justify, okay? And so they don't tell us to, but maybe step 1, we draw a diagram. So we've got a horizontal road or circle. So again, just like our previous example, if you draw a side view, you're going to not really see a circle because that's 3-dimensional from the side. You're going to kind of see an ellipse. So this is a side view. Top view, we can draw that as well, but really you just need one, okay? And so where's the car? They don't tell us if it's on the left side or right side, so pick one. I would not pick, you know, the back side of the circle or the front side of the circle. Those are a little harder in a side view. And so we'll just say our car is here. And it's coming towards us, it's going away from us. Remember, it's moving in 3 dimensions. And so what forces are acting on the car at this moment? We got gravity always down. Normal force, perpendicular to the surface. It's a flat horizontal road, so normal force would go up. How big do I draw it? It's going to actually be the same here, right? Kind of old school. It's going to balance, equal and opposite to balance out. This car on a horizontal road hopefully doesn't have any vertical motion. Here's a review question. These two are equal and opposite. Newton's first law. The balance game on a single object is the first law. Question? Well, we just saw one going over the hill where we said gravity was bigger than your. So here I explained it as gravity center seeking. Center seeking to make the circle has to be bigger. Whatever label, whatever force is towards the center, it's always going to be greater than the center opposing. Because if it's not, you're not making the circle. Does that make sense?
Yeah.
Center seeking versus center opposing.
Like gravity is always the same, right?
Gravity FG at all points is the same mg. Yes, but normal force doesn't have one equation. Tension does not have one equation. They can vary. They're dependent on whatever the situation is. And so even go back to like the elevator situation. Normal force varied based on your motion. Were you going up? Were you going down? Were you speeding up, slowing down? Normal force varied, okay? And so in our circular motion, if you learn anything from today, center seeking is always bigger than center opposing. Okay. But in this one, it's a horizontal circle. Fn and Fg are vertical forces, so they're not going to contribute to the circular motion. So they're good old-fashioned equal and opposite so that we don't have vertical motion when you're driving on a roundabout, right? And so if they're not going to contribute, who does? Friction. And so last time I walked around the room, I made a circle, I talked about grip. If I didn't have grip, would I make the circle? Maybe, maybe not. It depends on my speed. And so that center seeking force, it doesn't feel, maybe you're thinking, well, shouldn't it go another direction? Ask yourself this question. Without that center seeking force, you would not make the circle. If you don't have grip with the road, you're not going to make the circle, okay? And that's it. If you wanted to say, oh, well, shouldn't there be a kinetic friction, maybe to slow me down linearly? That one would be hard from a side view, right? If the car is coming towards us, it would be drawn in the third dimension, so you can ignore it. Either way, it's not part of circular motion. It's not part of the center-seeking direction. And so, FNet statement, by the way, it's the same diagram, whether there's ice on the road or not. Tom, is he here? Okay. There's ice on the road or not, it's the same diagram. Ice can still have some grip, right? 0.25 is still something. Okay, same diagram, same FNet statement. All we're going to change is that coefficient of friction. And so, step 2, FNet statement. FNet centripetal, sum the forces that are center seeking. It would be what? Just friction. Again, gravitational and normal, they're not part of a horizontal circle. They're vertical forces. And so that's it. It's center seeking, it's positive, done. Now we can actually start solving. Wait, what do we solve for? How do I make it on the curve? There's not a yes or no answer in an FNet statement. So what do y'all think we should solve for? How do you know if this car on this road traveling at that speed, how do we know if it's going to make the circle? Kind of like the car on the hill, the ball on the string. What if we solve for the speed and then compare it to that 14, our actual speed? Okay. What if we find the minimum speed, or actually here it would be the maximum speed based on your level of friction. And then we compare it to the 14. Good deal? So we're going to solve for the velocity, and I don't see the velocity, so Newton's second law, MAC equals, review time, what's our equation for force of friction? Coefficient times normal force. So remember, it's that mu s times the normal force. And what did we already say about the normal force? It's equal to our gravitational force, so I can sub in mg, bring everybody else down. What do you notice? I can cancel mass. Now they gave it to us, so that's okay. You can actually, if they had us actually find the frictional force, then we would need the mass. But here I said we're going to be solving for the speed for comparison. And so mass cancels when you solve for the speed. And I don't see speed yet, so next step, centripetal acceleration, we can plug in v squared over r equals mu s g. And we're going to solve for v. So kind of familiar, multiply both sides by r, take the square root, but now I got a mu s in there. And that's going to be our working equation for both part 1 and part 2, whether it's dry or icy. We're just going to plug in a different coefficient. And so the velocity when it's dry is going to be equal to the square root of 0.6 times 10 times the radius, which they said is 50. And so work that out and let me know what you get. 17.3. Now hold on to your comparison. Hold on. What about when it's icy? 0.25 times 10 times 50. 11 point what? 1. Okay. And so there's our two speeds when it's dry and when it's icy. Now, a little bit of review of static friction with mu Fn. Do y'all remember this graph? Y'all remember that one? And so when you're at the maximum, if you remember, we said that our equation is actually 3 equations in one. When you actually do mu s times Fn, you're finding a maximum amount of friction on this graph, okay? Remember the 2 finger, 4 finger, 6 finger, 8? If 8 fingers is your maximum to stay in grip with the ground, then that's a maximum static friction. So it's a maximum velocity under the dry condition. It's a maximum velocity in an icy situation. Now we're going to compare with the given V actual, they said was 14. And so if your V max in a dry is 17, but you're actually going 14, are you going to make the curve or are you going to skid off the road? You're going to make the curve. So you would be safe. You'll make the curve. But now there's ice on the road. Your maximum speed that you can go and still have grip with the road and be safe is 11, but you're going 14. What's going to be the result? Hi, Mom, Dad, can you call AAA to come get me? You are going to skid off the road. Now, hopefully you're still safe. Hopefully you're still safe, okay? But you're going to skid off the road. You will not make the circle, not make the circle. So this one's similar to your limits that we talked about with min and max speed, but it's got friction involved, okay? And different conditions. Is this making sense? Roadside assistance. I don't know. It may be an old school thing now. I don't know. But okay. Let's see if we can do, actually, let's put y'all to the test. We got, 10-ish minutes left before announcements if they come on. Let's see if y'all can work together on number 10. So just to give you a heads up, we're at the top of a flat building And we're going to tie a dummy to a rope and spin it around. Where's the physics? Where's the physics? In a vertical circle. Okay, so if you want to, not hurt the crash test dummy, which has no life, right? Okay, if you want to make it more friendly, it's a ball on a string. There you go. But it's a vertical circle. Diagram F net. Notice what you're finding. What's the maximum speed? What's the minimum speed? See if y'all can do those. Good deal? And I'll walk around and answer questions if you got them. But give it a try. Work together.